Welcome, everyone, to this month's installation of our UQ TTA seminars series. And it's a pleasure for us this time around to have Professor Jinlong Wu from the University of Wisconsin-Madison. Professor Wu got his PhD from Virginia Tech in 2018. As I mentioned, he's now an assistant professor at the University of Wisconsin at Madison. And his work focuses on sort of the intersection of fluid mechanics and machine learning and uncertainty quantification, all things that are, I think, very relevant to this group and very important. And in particular, has made some really notable contributions in the physics-informed machine learning space for turbulence and for fluid mechanics more broadly. So, without further ado, I will turn it over to Jinlong to share his work on learning stochastic closure models for complex dynamical systems. So, the floor is yours, Jinlong, and thank you for joining us.
Thanks, Mike, for the introduction, and also thanks for the invitation. So, good afternoon, everyone. Today, I'm going to share some recent progress about learning stochastic closure models for complex dynamical systems. So, the general motivation of this work is that in many science and engineering applications, we have complex dynamical systems with multiscale and multiphysics processes. For example, the Earth system, renewable energy harvesting, autonomous systems, and also additive manufacturing. So for all the systems, we have multiscale, multiphysics processes that most likely we won't be able to resolve every piece of detailed information. So taking the Earth system, for example, we have the cloud microphysics at millimeters, and we also have turbulence at a range about 10 meters to 100 meters. But at larger scales, we can have planetary waves up to 10,000 kilometers. So in nowadays, or in foreseeable future, resolving every piece of details within this complex dynamical system seems to be almost impossible. And that's why closure models are usually needed for some unresolved degrees of freedom of those kind of complicated systems. And the general theme of this track of research is about how to improve closure modeling for complex dynamical systems using data-driven methods. Okay. So before getting to the detailed methods, let's take a brief introduction about the closure model or closure problem. So let's imagine that for the original system, it takes this general dynamical system form. So here, small v corresponding to the original system state, and it can be very high dimensional. And for the m here, it characterizes the dynamics of the original system. And just because we won't be able to directly simulate this original governing equation for many realistic problems. And that's why people often come up with some reduced order system state by, for example, applying cross-graining, PCA, or more recently autoencoder. And in order to, instead of looking at the small v, the original system state, now we have a reduced order representation. As long as we choose how to kind of get this reduced order representation, it will be not difficult to just kind of manipulate the original equation and try to derive a governing equation for the reduced order system state, capital V here. And m bar here corresponding to the dynamics of the reduced order system. The tricky part is that the original dynamics m is usually nonlinear, which means that the m bar here, most likely, it will not only depend on the capital V, but also depend on the small v that corresponding to something that we don't want to numerically resolve. And to describe the impact of all those unresolved physics, that's the place where closure models are needed. And the closure model means that we want to come up with some m tilde. And this m tilde will just only depend on the reduced order system state, capital V, and we will hope that M tilde can well approximate the original dynamics for the reduced order system, the M bar here. But it turns out to be that for many realistic problems, this kind of approximation does not hold true, and that motivate people in recent years try to use an additional term and try to characterize the difference between the M bar and M tilde. And this correction term is indicated by this U term here. And for most existing works, people tend to assume that this U term takes a deterministic form. But that also leads to some questions. For example, if we think about the molecular dynamics and heat transfer, and in order to model the heat transfer at the macro scale, the large scale, we don't need to resolve every piece of details of the molecular dynamics, of course. That's because we have a clear scale separation between these two, the large scale and the small scale. So that's the key reason that a deterministic macro scale model can well kind of characterize everything kind of happening at the large scale. But for some other systems, for example, for the cloud dynamics, as we can see in this illustrated figure, we will have some large scale of the cloud motion, but we would also expect some very tiny scales, for example, the microphysics that contains the raindrop or the snow. So which means that the kind of scale separation here is large, but more importantly, there is kind of a continuum of kind of scales of processes that connecting the smallest one to the largest one. So which means that we cannot simply kind of get rid of some unresolved kind of physics and try to use a deterministic term to characterize that contribution. And then motivate people in recent years to think about how we can go beyond the deterministic closures. And choice is that we can add a stochastic term. And if we want to learn both the deterministic correction U here and also the stochastic term that driven by the standard Wiener process W, the learning process here actually corresponding to a standard parameter estimation problem for SDE. And this is a field that has been studied for decades. And I just listed some recent works, but actually the literature here is much more than that. But for our work, we try to target at a more challenging scenario. The reason that we said it's a more challenging scenario is because first we assume that we only have a limited amount of indirect data. Indirect data means that we only have, for example, moments or autocorrelation for the reduced order system state. And we also assume that those indirect amount of limited data is noisy. And we also don't want to assume that we have very high temporal resolution data, which means that data can be very sparse in time. And in addition to all of those challenges about the data, for the model part, we also don't want to assume that M tilde is readily differentiable. So which means that we don't assume that we have an existing differentiable solver for the kind of traditional kind of closure term. And that kind of motivate us to use a different kind of strategy to solve this optimization problem. And for this specific work, we use the derivative-free optimization method. Specifically, we use the ensemble coming inversion. So before getting to some detailed results, I'm going to first briefly introduce this ensemble coming inversion, the EKI method that we're using here. So this method was developed by some researchers about 10 years ago, and the inverse problem to be solved is presented at the top as a general form. So here, theta corresponding to some unknown parameters that we want to estimate, G corresponding to some forward model, and Y corresponding to some data that we can obtain, eta here corresponding to some noise that associate with the data action. Okay. So for the EKI updating formula is presented in the middle, the J here corresponding to the index of ensemble, and M here corresponding to the index of EKI step. As you can see here, the updating formula for EKI actually is an iterative process. And it can be understood in a quite intuitive way, assuming that we already have the theta estimation on the parameters at the M EKI step. And with this current estimation, we can first plug it in the forward model so that we can get the output. And most likely, this output will not perfectly agree with the data Y. The first step, we calculate the mismatch in data space. And secondly, we use some matrices, try to do normalization for this mismatch. More specifically, this CGG here corresponding to the covariance matrix in the data space that is estimated by the ensemble members of EKI. Gamma here corresponding to the data noise. And we have a matrix inverse here indicate that we try to normalize this data mismatch using this kind of summation of matrices. And with this normalized version of mismatch, we further use the covariance matrix between the parameter space and also the data space. We use this covariance matrix try to help us project the normalized mismatch back to the parameter space, such that we can use this projected mismatch in order to update our current estimation of theta, so that we get the new estimation theta, what we call theta at m+1 EKI step. So we will use this iterative method for multiple times until the statistical convergence is achieved. And there are a few advantages of using EKI. The first and most important one, as you may notice, that for the whole updating formula, we don't require this forward map G to be differentiable. And secondly, EKI has been proved to be robust to noisy evaluations of this forward map G. And also the core task here is equivalent to a convex optimization problem, which means that if we want to incorporate some additional constraints about the unknown parameter theta, for example, the sparsity constraint or some physics constraint, we can do that in a quite efficient way by formulating a constrained convex optimization problem. As today's talk's focus is not the EKI method, I'm not going to cover all the details about those advantages. So in this track of work, we just use the EKI as a derivative-free optimization tool to help us estimate unknown parameters in our stochastic closure model. Okay. So after introducing the EKI, let's take a quick look about example. So the example I'm presenting here is the Lorentz 63 system. It's not the standard one, but it's the one that projected to the POD transformed coordinates. And after this projection, the key feature about this new system is that the third dimension, the A3 variable, only contain a small portion of the total energy of the whole system. So more quantitatively, it contains about 5% of total energy of the whole system. So if we need to build a reduced order model, a straightforward idea is that just because A3 contains a small portion of the energy of the total system, let's just throw it away. So if we do that, then the reduced order model becomes a two-dimensional system that only contain the A1 and A2 states. And this is a classical example that was studied by Professor Tim Palmer more than 2 decades ago. And Professor Palmer found that for the true system, of course, is still a Lorentz 63 system. So it has this chaotic behavior and also the butterfly shape of the trajectories. But he also found that if we use the straightforward idea to throw away the third dimension, build a reduced order system for A1 and A2, and then the system will lose the chaotic behavior, as we can see at the bottom. But more interestingly, Professor Palmer also found that if we try to just add some very simple stochastic term, such as white noise, at least we can qualitatively get this chaotic behavior and butterfly shape of trajectories back. So inspired by his findings, in our work, we try to more systematically learn stochastic corrections to the reduced order model such that we can get more quantitative agreement with the true system. And more specifically, we try to introduce both the deterministic correction terms U1 and U2, and also stochastic correction terms driven by standard Wiener process to both A1 and A2 dynamics in the reduced order model. And the data that we're using here is indirect data, contains first to fourth order moments of both A1 and A2, and also autocorrelations of them. And more specifically, we parameterize U1, U2, sigma 1, sigma 2, all those unknown functions using some kernel methods. And we try to use the EKI optimization tool that we just introduced in order to help us learn the unknown parameters of those kernel methods that help us characterize U1, U2, sigma 1, and sigma 2 here. Okay. So I'm going to skip some detailed results, but only show the key results of our work. So here at the bottom, we present the probability density function of both A1 and A2 in some field. People also call that invariant measures of A1 and A2. So that means that we simulate the reduced order system for long enough time and just try to plot the probability density functions for both states. And as we can see, compared to the results, the empirical results obtained by Professor Palmer more than 2 decades ago by just adding the white noise, if we more specifically introduce the stochastic closure term and use data to calibrate those stochastic correction terms, we will be able to achieve a more quantitative agreement with the true system. Okay. So at the bottom, I list the coming version method junior package that developed by my former colleagues at Caltech. So in more recent years, I also want to emphasize that the progress on the generative AI part also provides various types of tools to build a probabilistic closure model from data. So that's why for the rest of this talk, I will focus on some recent developments of closure modeling by generative AI methods, such as diffusion models or the flow matching. Just because these two are very closely related to each other, I will just focusing on introducing the results related to the diffusion models, but just want to point out that actually these two things are related to each other. There is no huge difference between these two. And for this type of work, before getting to the detailed method, I would like to give a very quick review about all the existing tools that we engage in our method. So the first thing, of course, is the diffusion model. More specifically, I'm introducing the score-based diffusion model that was developed by Yang Song a few years ago. So similar to some other generative AI methods, essentially, the key concept here is try to build a forward and backward map between the target distribution at the left side and also a Gaussian distribution at the right side. The reason that we want to do that is Gaussian distribution is much easier to draw sample from. And for the score-based diffusion model, we were promised that as long as we can find this kind of highlighted kind of box term, what people call score function, and then we will be able to solve the reverse SDE and then just kind of bring any sample from the Gaussian distribution at the right-hand side to the corresponding sample at the target distribution. Okay. And this is achieved by what people call score matching, and the optimization objective is presented in the middle here. And the tricky part about the score matching here is that it involves the use of the true score function, which is often unknown to us. And in order to make the kind of optimization problem tractable, people try to develop the what called denoising score matching. Instead of targeting at the smallest difference between the model score function and the true score function as the standard loss term, now we're looking at a target that only engage a transition density. So we can assign this transition density by ourselves. And then with this kind of denoising score matching loss, we will be able to solve optimization problems such that we can get an approximation of the score function model S here. Once we get that from the training using sample of the data from the true distribution, we can plug in this approximated model of the score function as back to the reverse SD so that we have the map that can help us bring any sample from the Gaussian distribution to the corresponding one in the target distribution. Okay. So until now, we're still talking about unconditional sampling, which means just bring an arbitrary sample in the Gaussian distribution to the target distribution. But more recently, people also try to develop on the kind of ability of that unconditional sampling using score-based diffusion and try to introduce the conditional score matching. So you can see that the loss function here that we try to solve the optimization problem are almost identical to the unconditional one. The only difference is that we try to embed the conditional information y in most cases that corresponding to some data that we can get. We incorporate this information in both the input of the score model and also we kind of incorporate in the sampling process when we draw samples in the training part. Okay. And the score function obtained by minimizing this loss function can be used to draw samples from not just the unconditional target distribution, but a conditional target distribution of U conditional Y on any information that we want to use. Okay. So this is still a quite general work, and we use this general tool in our work together with another existing tool, what people call the Fourier neural operator. So for Fourier neural operator is operator learning framework that try to build the map between function spaces. More specifically, here I present just one Fourier layer. As we can see that for the upper path, we have kind of the Fourier transformation to get into the Fourier space, and we do linear transformation in Fourier space and then transform back to the original space. So for the bottom part, we have the bypass that just do the linear transformation in the original space. And we add these two things together. That's kind of the most fundamental building block of the Fourier neural operator. And the good thing about that is using this Fourier transformation and linear transformation in the Fourier space and transform back, we will be able to model some kind of non-local mapping. Okay. So after introducing these existing tools, I think it's time for me to briefly go through the summary of our approach. So recall the motivation here. The motivation here is that given the reduced order system presented at the bottom, we have the existing model M tilde, which we believe is not good enough. And we want to kind of introduce a correction term. And instead of kind of assign deterministic values of this correction term every time step, we try to draw samples from a target distribution. And in order to achieve this sampling procedure, we make use of the score-based generative model. So essentially, we build a score-based generative model that can help us to kind of do forward and backward mapping from the distribution to the Gaussian distribution. And basically, once we train this model, we can draw samples very easily from the Gaussian distribution and just run the reverse SDE and get a corresponding sample for the target distribution of the closure term. And then we can just plug it back into the physics-based solver, try to help us correct its simulation results. Okay. And more specifically, we engage the Fourier operator here, Fourier neural operator here, try to help us characterize the score function. Of course, in our case, the score function, both input and output, contains the spatial temporal fields of the closure term. So that's the key motivation why we engage the Fourier neural operator to help us characterize the score function. And we design the architecture in a specific way that the input of this Fourier kind of surrogate score function can take both kind of current and previous time steps of the reduced order system state. And it can also incorporate some sparse real-time kind of measurement data if they are available. Okay. So here is just a very quick summary about all the key components of our stochastic closure model using the score-based generative model. And before getting to the detailed results, let me quickly summarize some highlights of our approach. The first one is that the data Y contain both previous and also current snapshots and spatially sparse observations from the prediction step, which means that is an approximated way or empirical way to do data assimilation, if you want to call that in this way. And in this work, we also use Fourier neural operator to construct the score function S, which facilitates building a nonlocal model if needed. And this leads to a stochastic and nonlocal approach for closure modeling while score-based conditional sampling. So after introducing all the kind of details and highlights of our approach, let's take a quick look at a simple example here. So the example that we study the performance of our approach is just the two-dimensional Navier-Stokes equation. For the original equation, we deal with the vorticity equation. So here, omega corresponding to the vorticity and is stochastically driven for the true system. And we also have a forcing term F here. And we have the convection term here that U corresponding to the velocity field. And for this toy example, we consider two different scenarios. The first scenario is that we assume the diffusion term and also the stochastic term, the summation of these two are unknown to us. The second scenario that we consider is that the convection term and the stochastic term, both of them are unknown to us. Okay. And the key difference between these two scenarios is that the first one essentially will give us a local map between the omega and the unknown closure term G. But for the second one, theoretically, it should give us a non-local dependency that we can better demonstrate the capability of the Fourier neural operator component. And the key reason here is because the u, the velocity vector here, actually is governed by what people call the velocity Poisson equation, that the curl of the vorticity becomes the source of that equation. So which means that the relation between u and omega actually is non-local, and that's why h will theoretically non-locally depend on omega. So before directly plugging the data pairs and try to train the score-based diffusion model, we use the Pearson correlation to try to numerically verify the local and non-local dependency that we just kind of briefly introduced. So here, the C corresponding to the center point, but just because for this two-dimensional problem, we do enjoy some symmetry. So which means that actually we can kind of pick this center point of X at different location and then try to evaluate this Pearson correlation and try to do averaging to get a more robust results to reflect the essentially the dependency between the closure term and also the vorticity, omega, the system state. And here I present the field of the Pearson correlation that we obtain by averaging many calculations. As we can see here, the dependency between G and omega, as we can see that it decay very fast from the center to the nearby region, which confirmed that the dependency here is local for scenario 1. But for scenario 2, as we can see that the Pearson correlation shows a much stronger non-local dependency of the H on omega. So for the rest of the results for this problem, I'm going to focus on the scenario 2. And the first set of results I'm presenting here corresponding to the generative samples of the closure term. As we can see that the top row corresponding to the benchmark truth. The second row corresponding to the testing kind of situation that we test on one different resolution compared to the training resolution, and the bottom row corresponding to another testing scenario that we choose an even kind of higher resolution. And as we can see that both the middle and the bottom rows agree pretty well with the top row, which confirm the resolution invariance property of the Fourier neural operator, which accounts for one of the advantage of using the operator learning here. And for this set of results that corresponding to that we engage the trained score-based diffusion model that we can draw conditional samples of the closure term condition on the information of the system state, the vorticity. Once we draw the samples, we plug it in to the governing equation for the vorticity and try to do the simulation. So here shows the simulation results of the vorticity. The top row shows the true results. The second row shows the simulation with the closure term H trained by the score-based diffusion model. And the bottom row shows the simulation that we just neglect this H term completely. And as we can see that the middle row agrees much better with the truth, and the bottom row indicate that the H, the toy closure term here actually plays a very important role. If we throw that completely away, and then basically we will have some boring dynamics. And here presents some kind of more detailed results that we just calculate the arrow field of the simulated vorticity using the simulation with the score-based kind of sampled closure term H, and also the simulation without this H term. As we can see that we can maintain the arrow of the simulated vorticity field in a relative kind of low value for a certain amount of time, which demonstrates the promising kind of side of the proposed approach. So that corresponding to the summary of our approach that we first kind of do a generative AI-based sampling and try to sample this closure term directly. But that means that this sampling needs to be done at every numerical time step of the physical solver, which means that every kind of dt at the bottom, we need to kind of draw a sample from this score-based generative model in the closure space. But for this closure term, in many problems, it can be within a high-dimensional space with a lot of degrees of freedom, which means that this kind of coupled simulation will be very costly. And that motivates us to further think about doing a kind of faster sample kind of procedure. And in order to achieve that, the key concept here is that we try to replace everything, not only the closure term that we want to draw a sample, but also the information that it condition on. We replace both of them with their low-dimensional latent representations, such that we can just kind of train the score-based generative model and also draw samples from that in a low-dimensional latent representation to save us some computational costs. And we tried this approach in a naive way. So the naive way means that if we train an autoencoder first and then train the diffusion model in the latent space, we found that sometimes well-trained autoencoders to encode the closure term and also the vorticity field can lead to very bad performance of diffusion model training. On the other hand, we have already demonstrated that the training and also the sampling in the physical space of the closure term actually provide very good results. So that motivates us to investigate a little bit because as engineers, we don't like kind of a model. Sometimes it works, sometimes it don't. And for this kind of latent naive training approach, we try to kind of improve that with what we call the joint training, which means that for the autoencoders and also the diffusion model, we just kind of joint train both of them. And in this case, we managed to show that consistently the results will be improved a lot for the quality of the sampled closure. And with this kind of empirical results, we try to ask ourselves a question, why? Most likely, we need to kind of dig deeper into the two different latent spaces. And in order to achieve that, we use a common technique, what people call t-SNE plot, to visualize the physical and also latent spaces and to investigate the reason about the performance difference here. And at the bottom here, I just show the very standard illustration of t-SNE. So for the handwritten digits, if we encode that with 64-dimensional vector, for example, it's just 8 by 8 pixels, we will not be able to visualize directly in this 64-dimensional space. And t-SNE provide a way to just compress this 64-dimensional space to a 2-dimensional space. But it does not arbitrarily compress this higher dimensional space to a lower dimensional one, but it tries to maintain the relative distance between two different things in the original space and try to maintain this distance in the lower dimensional space. And that's why if we take a look at the t-SNE plot, the same kind of handwritten digits will tend to cluster close to each other in this reduced order space. Okay. So we use this technique, try to help us visualize the latent spaces that we got from the bottom results. And here we show the t-SNE plot for the latent space results and also for the physical space results. Not only for the vorticity, but also for the distribution of the closure. We also investigate the distribution, joint distribution of the closure, and also the vorticity and the conditional distribution. And what we found is that if we do latent space with joint training, and latent space the relative closeness got maintained pretty well compared to their physical space counterpart. But if we do the naive way two-step training, first we train a very well-performed autoencoder, and then we just train a diffusion model in that latent space. Sometimes the first step trained well-performed autoencoder that encode information of omega and h. It could distort the latent space a lot, such that training a diffusion model in that latent space become a much more challenging task than just directly training the diffusion model in the physical space. Okay. And inspired by this finding, we also try to introduce some more direct regularization about latent space. The first approach is what we call the MP. MP here stands for the metric preserving. And the second approach is what we call the geometry aware. And to provide you some intuitive background, the first one actually, we try to maintain the relative distance in a metric using the Euclidean distance. But for the second one, we make full use of the shape of the data and we use the manifold distance. Okay. And as you can see that for the latent joint training, also the latent space that regularized by Euclidean space closeness and also the manifold space closeness of the original space. For all those methods actually corresponding to regularizing the latent space to ensure that it perform well with the diffusion model training. But they belong to two different perspectives. The first one is an implicit way, but the second one, the latent space regularized with Euclidean distance measure and also the manifold distance measure, both of them actually an explicit way to incorporate the regularization. And we also investigate the performance of the later two methods in the sample quality. Both of them achieve very good performance. I skipped the results here. I only show the comparison of the t-SNE plot. That explains why we get good performance of the trained diffusion model in those two latent spaces. That's because the latent spaces does not distort a lot compared to the original physical one. And one additional take-home message that I want to make here is that explicit regularization of latent space tend to be easier to train than the implicit regularization, which means that we do a joint training together with the diffusion model. Okay. So to summarize, many complex dynamical systems involve multiscale dynamics without a clear scale separation, for which stochastic closure modeling is promising when simulating those systems. And in this work, we demonstrate that derivative-free common inversion methods enable learning of stochastic closures in very challenging scenarios, such as sparse in time and noisy data, non-differentiable physics-based solvers. And also we demonstrate that a stochastic and nonlocal modeling approach can be achieved by combining some widely used existing tools, such as score-based diffusion model and Fourier neural operator. For this part of results, we assume that we have standard regression type of training data, but my students have some recent works. We are trying to wrap up a paper that also tests this type of modeling approach in the indirect training data scenario. And the paper should be appear online soon. And also for the latent diffusion models, we found that they can offer faster sampling and significantly enhance the efficiency of the stochastic and nonlocal modeling approach in the context of closure modeling. And also we perform a systematic study for both implicit and explicit regularizations of latent space in order to ensure a good performance of the sample closures. And at bottom, I listed several papers that related to all the topics covered by today's talk. So with that, I'm happy to take any question. Thank you.
So I could not follow the manifold-based distance. Could you
Yep.
please explain that again? Because the manifold seems to be unknown yet.
The manifold here is more like a approximate kind of manifold. It's more like manifold kind of described by the data samples. So for the data samples, it will have some kind of geometry structure already. So we can always embed kind of this in a high dimensional kind of Euclidean space. But as long as it has kind of low dimensional kind of shape of the data kind of samples, we can kind of use existing tools to calculate the manifold distance, try to leverage this kind of geometry information.
Yeah, so could you please elaborate then how do you actually compute the distances?
That's a great question. That's actually a technical detail question that I would encourage you to check our paper here. So the short answer is that we use a standard package to calculate this manifold learning.
Okay, okay, thank you.
Yeah, yeah. Thanks for the
Great
question.
job. Yeah.
So, Jinlong,
Yep.
if you don't mind, I can have a question.
Sure, sure.
Yeah. So what is so when you train a conditional diffusion model, how many data points do you have for training?
So how many data points? That's a good question. The original work got published 3 years ago. I forgot the detailed number. I may need to double check. But for this system, actually, it's not that kind of intrinsically, it's not that very kind of complex because it's kind of a toy example with just the two-dimensional Navier-Stokes, not very high Reynolds number. So intrinsically, it does not require huge number of training data points. What I can promise you is that we're definitely not looking at, for example, more than million kind of data samples, much less than that.
Yeah. Well, it will be good to know because I suppose conditional diffusion models will require pretty extensive data points, and if you're using simulation, then it really do not do so well if you have complex models.
Yeah, but I would argue that it all depends on the intrinsic kind of degrees of freedom and complexity of the data set. For this
Yeah.
problem, it happens to be that although it's kind of turbulence kind of example, but it's a very toy one and at relatively low Reynolds number. But that's a very good question. So for kind of more challenging problems, we would expect that the model that we present here will be data hungry. But for this data hungry issue, this could be addressed by some kind of other approaches. For example, we can always kind of engage regularization or kind of known physics, yeah, to kind of fill in the gap if we don't have sufficient amount of data. But that's a good question.
Mm. I mean, another question related. You mentioned flow matching models, but didn't discuss too much. One difference between flow matching and score-based diffusion models, is that if you do flow matching, the sampling is really fast. You mentioned this computing cost as a bottleneck in your approach. Have you tried flow matching?
Yes, yes. In our recent works, we also kind of engage flow matching. And you're definitely right. The sampling kind of speed, faster sampling speed of the flow matching, although these two kind of framework, yeah, theoretically equivalent to each other, but faster kind of sampling speed using a deterministic ODE kind of reverse process. That's something we explored kind of in our recent paper. I think the top one.
Okay. All
Yeah.
right, thanks. Well, anybody, if you have other questions, please just unmute yourself. Well, if there's no more questions, then let's thank our speaker again.